In the last video, we started talking about acid-base strength, right? We said that stronger acids are more ionized than weaker acids, right? A strong acid is going to ionize completely, where a weak acid is only going to ionize partially. And then not all weak acids are equally weak, right? Some are stronger than others. In this video, we're going to start looking at factors that affect that. The factors that affect acid strength. And just kind of to remind ourselves, what we're looking at here is that stronger acids ionize more than weaker acids. Right? If it's a strong acid, it's ionized completely. And then if you were to compare one weak acid to another weak acid, the one that ionizes more is a stronger weak acid. Right? If I was to take HA, I'm just using A as a generic anion, and I produce H plus and A minus, right? What I'm doing, I'm just going to redraw this here real quick because I want to show that bond, is I'm breaking this bond. Right? If I'm going to ionize them, right, if I'm going to separate them from each other, I need to break that bond between the hydrogen and then whatever the anion is. The stronger that bond, the harder it is to break, the weaker the acid. The weaker that bond, right, the easier it is to break, the stronger the acid. So stronger acids have weaker HA bonds, right? They're going to ionize more, which means it's easier to break that bond, meaning the bond is weaker. And then weaker acids have stronger HA bonds, right? It's more difficult to break them. It's going to be ionized less. What we want to look at next, right, are what make one bond stronger or weaker than another. So a couple trends we're going to look at. Our first one are for binary acids. So binary acids are just having two types of atoms in them. So HCl, HBr, so just two different types of atoms. So binary acids. So for these ones, as I go down a group on the periodic table, my atoms, right, that form that bond become more mismatched. If we remember valence bond theory from 150, 151, right, that told us that when we form a covalent bond, we're actually taking our orbitals and we're overlapping them, and those shared electrons are found in that overlapping region. And we said that they overlap better when they're similar in size. So if I was to compare, right, a bond between two hydrogen, I have an s orbital of one hydrogen, an s orbital of another hydrogen, they're overlapping, and those electrons are found in that overlapping region. If I was to compare a bond between hydrogen and fluorine, right, I have an s orbital for hydrogen, 1s, I have a 2p orbital for fluorine, and they're overlapping, and those electrons are found in that overlapping region. And this would be a stronger bond between the two hydrogens, right? Because the size of those orbitals are very similar and the shape of those orbitals are very similar. This would be a weaker bond, right? Because the size and the shape of those orbitals are more mismatched. So stronger bonds, right, And we're talking covalent bonds. We should probably add that. Stronger covalent bonds, right? We're not sharing electrons if it's not covalent, right? Ionic bonds, one atom is losing them, another atom is taking them, and we have oppositely charged atoms attracted to each other. Are formed from similarly sized and shaped orbitals, right? The more mismatched the orbitals are that are forming the bond, the weaker that bond. More mismatched orbitals equals a weaker bond. And again, this goes back to valence bond theory, which you would have talked about in chapter 4 of 150 or 151. So it's probably been a little bit. So again, kind of going back to binary acids here, I wrote this and I got off on a review. As I go down a group on the periodic table, remember that the size of our occupied orbitals are getting larger and larger and larger, right? If I look at fluorine, its outermost, right, its valence shell is shell 2. If I look at chlorine, it's 3, bromine, it's 4, iodine, it's 5. So as I go down, the size of that orbital that's overlapping with the s orbital of hydrogen becomes larger and larger and larger. That bond becomes more and more mismatched. It becomes weaker and weaker. My acid becomes stronger and stronger. So let's write some of that down, right? As we go down a group, in the periodic table, the size of the atom, essentially the atom's valence shell, valence shell orbital, we should say, gets larger. So the bond with hydrogen, right, with hydrogen's s orbital, is more mismatched and thus weaker. So as we go down a group in the periodic table, the size of that anion is going to be the important factor, right? As I go down a group, size is going to be my factor. We're going to have a different trend as we go across a period, but as I go down, my atom, right, its valence shell, its valence orbital is getting larger and larger and larger. And we should say valence orbitals, it's not just one, but so kind of an example, right? HF, we said was a weak acid. HCl, HBr, HI. This is a weaker bond, which means stronger acid, right? HCl, HBr, and HI are all strong acids, but HI is the strongest of those three strong acids because its bond is weaker, right? If we wanted to draw some kind of not at all to scale, funny little pictures, my s orbital and then a p orbital, my s orbital, and both lobes of that p orbital should be the same. An artist I am not. A bigger p orbital, s orbital still the same size, a bigger p orbital yet, an s orbital, my s orbital just got smaller, my s orbital, and an even bigger p orbital, right? Weaker and weaker bond because that anion is getting larger and larger and larger, right? F minus, Cl minus, Br minus, I minus. larger anion. More mismatched bond. Easier to break. As we go across a group of the periodic table, we're actually going to look at electronegativity instead of size. So as you go across a period, and I am going left to right, the electronegativity of the atom is going to be our factor. So we'll say anion again gets more electronegative. And then again, remembering back to polar bonds, right? If I was to look at a bond between hydrogen and fluorine, fluorine is more electronegative than hydrogen. If I'm to look at a bond between hydrogen and oxygen, right, I'm going across a period now, so I'm comparing like carbon, nitrogen to oxygen to fluorine. Also polar. You know, water would probably be my example acid here, right? So I'm just drawing a bond. I'm not drawing the entire acid. A bond between nitrogen and hydrogen, and then a bond between carbon and hydrogen, right? Carbon-hydrogen bonds we actually usually consider as being non-polar, so I wouldn't even label those. But in these three cases, the electrons are being pulled towards my more electronegative atom. And not all polar bonds are equally polar, right? Because fluorine is more electronegative than oxygen, and because oxygen is more electronegative than nitrogen, fluorine is going to actually pull on those electrons stronger than oxygen is, and oxygen is going to pull on them more than fluorine is, right? Remember, if it pulls on them all the way, right? If it takes them, we have an ionic bond. We're closer to being broken. So this is a more polar bond. Right? If we were just to compare fluorine to oxygen to nitrogen to carbon, more electronegative. So more polar bond, easier to break. Right? Less polar, not polar. Stronger bond. So again, you know, kind of examples here, I'd be comparing, if I did like CH4 to ammonia, to water, to HF, stronger acids. Because the bond between the hydrogen and then what it's being ionized from, right? Remember, we're ionizing these, we're losing that proton. If it's a weaker bond, it's going to be easier to lose it. So kind of going back up here, just be really careful for these. As you go down a group, we're looking at the size, and that's really important because as I go down a group, it actually becomes less electronegative. It's more electronegative at the top. So fluorine's smaller, but it's actually more electronegative. So you want to be really careful to not get these trends goofed up, because if you do, you're going to get this first one backwards. So when you're going down a group, the most important factor is going to be the size of that atom. As you're going across a period, the factor that's going to be important is the electronegativity of that atom. So down, you're looking at size. Across, you're looking at electronegativity. We could make just like a little piece of the periodic table here and just try to summarize some of that if we wanted. So I'm going to have fluorine, chlorine, oxygen, nitrogen, and so on, just for orientation. So as we go in this way, right, it's becoming more acidic. as A minus, right? Just assuming a generic HA binary acid. So more acidic as A minus becomes more electronegative. And I'm going to run out of room, so we're just going to move this over a little bit. So as I go in this direction of the periodic table, right, from left to right, it's becoming more acidic as that bond becomes weaker, right? A minus becomes more electronegative. So weaker HA bonds, right? It's more polar. The weaker the bond, the easier it is to break it. If I'm going down, more acidic, as A minus becomes larger, right? So instead of more polar, this time it's more mismatched overlap, right? So again, weaker HA bonds. A different reason, right? My orbitals don't overlap as well versus electronegativity, more polar. But our trends. So again, as I go down, it's electronegativity we're looking at. Sorry, as I go across, that arrow goes across, it's electronegativity we're looking at, sorry. As I go down, it's the size that I'm looking at. A second type of acid, so these were for binary acids. A second type are oxo acids. So these ones, if I go back up, were for binary. So just two different types of atoms. Our second one is going to be with oxo acids, and I'll define that here in a second. So oxo acids are going to be acids that contain a hydrogen that's bonded to oxygen, and it can have a varying number of oxygens, and then also an electronegative atom. So kind of the general form, you're going to have H and then a Y. I'm just going to put some subscript there because it can vary, and then an O with a different subscript. So kind of an example, HNO3, right? H2SO4. I guess we could put a subscript on H also. HClO3. Those would all be considered oxo acids. Do note in all of these, the hydrogen that we're dissociating is bonded to an oxygen. When I write it, in this form, that's not really obvious. But remember when we're ionizing, right? So the bond that I'm breaking in all of these is between hydrogen and oxygen. And I will draw a couple out in a minute, but that's a big difference between that and binary acids, right? If I go back up and I compare just even these ones, for this first one, I'm breaking a carbon-hydrogen bond. Here I'm breaking a nitrogen-hydrogen bond. Here I'm breaking an oxygen-hydrogen bond. Here I'm breaking a fluorine hydrogen bond. So the bond that I'm breaking is different. With oxo acids, it doesn't matter if I give you nitric acid or perchloric acid, I'm always breaking an oxygen-hydrogen bond. So we do want to note that. So note, it's a hydrogen-oxygen bond that is broken, that is ionized for all oxo acids. So if I was to draw out nitric acid, right, if we were to draw its Lewis structure, I have nitrogen in the middle, and then I have, and it would have different resonance structures, but this would be one of the more common resonance structures. And if you remember your formal charge calculation, right, it has a net charge of 0, but I do have formal charge. So again, the hydrogen, and let's draw it out with an actual bond instead of not showing that. So I'm going to just redraw it where I put a line here, right? The bond that I'm breaking when it ionizes is going to be this bond. If I was to draw out sulfuric acid, I have sulfur in the middle. Sulfur is one of those atoms that can have more than 8 electrons around it because it has d orbitals available also to put electrons in. And when I draw its Lewis structure, this is what I get. I has 2 protons that I can lose, right? We can go from H2SO4 to HSO4 minus, and then HSO4 minus to SO4 minus, but both of those protons that I'm losing are attached to oxygens. So again, in oxo acids, it's an HO bond that's ionized for all of them. So some trends for us. Oxo acids that have different central atoms but the same number of oxygens. So kind of our first trend for oxo acids with different, I might have said the same, with different atoms Y. So nitrogen here is my Y in this case. Here it's sulfur. So different electronegative atoms that aren't oxygen, different atoms Y. A different central atom if you want to think about it that way. But from the same group, of the periodic table, and have the same oxidation number. What that really means for us is they're going to have the same number of oxygen atoms. If their oxidation number is going to be the same, then they're going to have the same number of oxygen atoms. You can think about it that way. So different Y. The Y is from the same group of the periodic table, and it has the same oxidation number, which means they're going to be bonded to the same number of oxygen atoms. So an example, if I was to look at HOCl, HOBr, HOI, right? Chlorine, bromine, and iodine are representing that atom Y. They're all in the same group, right? They're in group 7A. And if I was to assign oxidation numbers to chlorine, bromine, and iodine, they're actually going to have the same oxidation number. If you remember assigning oxidation numbers from 151, oxygen is a -2 unless it's bonded to fluorine in a peroxide. Hydrogen's a +1 when it's bonded to a nonmetal, -1 when it's bonded to a metal. And then the halogen, we just kind of had to figure it out. And we figured that out knowing that the net, right, the sum of my oxidation numbers needs to be the same as the charge on that compound or molecule. So since HOCl doesn't have a charge, I know that chlorine has to be a +1 for that to sum to 0. Right here, oxygen's a -2. It's not in a peroxide or with fluorine. Hydrogen's a +1 because it's bonded to a non-metal, which makes bromine a +1 for its oxidation number. And we could do the same thing with iodide. So the oxidation numbers will come out the same if they're bonded to the same number of oxygen atoms. Okay, so back to our sentence. So for oxo acids with different Ys, but the same number of oxygen atoms, the Ys are in the same group, the more electronegative the central atom, the stronger the acid. So for these ones, chlorine is more electronegative than bromine, which is more electronegative than iodine. So if we were to put a trend on here, these are going to be stronger acids. meaning the bond between hydrogen and oxygen is actually weaker in that case. So stronger acids. Another scenario for us, and this is for oxo acids that have the same atom Y, so the same central atom, but a different number of oxygen atoms. So for oxo acids, forgot an O. With the same atom Y, and again, you could just say central atom if that's easier. I don't like to use central very much because here, the way I wrote it, right, it's not my central atom. So the same atom Y, the one that's not oxygen or hydrogen. But with different numbers of oxygen atoms, the higher the oxidation number, on Y, the stronger the acid. Which happens to correspond to the more oxygen atoms that it has. So just kind of giving you an example here. If I had HOCl versus HO2Cl, so hypochloric acid versus chloric acid, right? I have chlorine, it's bonded to an oxygen and a hydrogen. Here I have, and let's actually do perchloric acid also, so 3 of them. It doesn't matter if I write it HCl, just if I'm confusing you guys, I don't mean to be. If I write it as HClO3, that's how it would have been on your list of like strong acids to memorize. That's kind of the typical form. It's the same as writing it that way. Those are the same thing. Neither one are the Lewis structure. Neither one's really correct. The reason I'm writing them this way is because I want us to remember that for all of our oxo acids, it's the HO bond that we're breaking. So I'm writing them that way so you can see a hydrogen bonded to an oxygen. When they're written this way, it looks like the hydrogen's bonded to chlorine, and it is not. So drawing structures for all of these, hydrogen bonded to an oxygen, which is bonded to a chlorine, and then that's actually bonded to another oxygen. There's lone pairs on these chlorines also. And you could do formal charge calculation. This would have a negative charge and this would have a positive. I'm not really caring if you put those lone pairs on here. I just want to be able to do our, I didn't mean to erase all that, our oxidation numbers. This one, remember we said why we could call it our central atom, because here it is in the middle, right? Those oxygens are all bonded to Y. So these are oxo acids that have the same atom Y, right? They're all chlorine, but they have a different number of oxygen atoms. This has 1, this has 2, this has 3. And we're saying the stronger acid has the higher oxidation number on Y. So we're going to assign oxidation numbers here. So we reviewed that just a few minutes ago. Oxygen we said is a -2 unless it's bonded to fluorine or inner peroxide. Hydrogen's a +1 when it's bonded to a non-metal, which oxygen is. And then the sum of our oxidation numbers must equal the charge on that molecule. The charge is 0, so this has to be a +1. This oxygen is a -2. This oxygen is also a -2. It's not in a peroxide or bonded to fluorine. Hydrogen's still a +1, which means this chlorine has to be a +3. A -2, a -2, a -2, and a +1. So this time for the sum of my oxidation numbers to equal 0, this has to be a +5, right? So my oxidation number on Y is a +1. Here it's a +3. Here it's a +5. The higher the oxidation number, the stronger the acid. So these are stronger acids. Just trying to make my handwriting somewhat legible. Stronger acids. So the higher the oxidation number on Y, the stronger the acid. That happens to correspond to the number of oxygen atoms. So the more oxygen atoms, the higher the oxidation number. And you can just use that as a shortcut instead of actually assigning oxidation numbers. So I would just recognize, well, this has more oxygen, so this chlorine is going to have a higher oxidation number compared to the other two, making that a stronger acid. So I do have an example for us, and I would like you to do this one on your own. So please hit pause, write this down, and then in each set you're going to identify, you can just circle it, the stronger acid. So please do that. After you're done, hit play again and you can check your work. Alrighty, so the first one, I have hydrochloric acid and hydrofluoric acid. You could actually answer this one based on the fact that hydrochloric acid is a strong acid, right? It's on our list of strong acids to memorize, where hydrofluoric acid isn't. Using our trends, right? If I gave you like hydrochloric acid and hydrobromic acid and we had to pick between those two, right? They're both strong acids. This is where we're going to look at the size of A. So I have hydrogen bonded to chlorine. I have hydrogen bonded to fluorine. Chlorine is larger than fluorine is, so that bond is weaker. Remember, valence bond theory tells us that the more mismatched the orbitals that are overlapping to form that bond, the weaker the bond. So weaker bond between hydrogen and chlorine than between hydrogen and fluorine, because chlorine is larger than fluorine. So more mismatched, weaker bond, easier to break it, so easier to ionize, right? The more it ionizes, the stronger the acid. In our next one, it's an oxo acid. We have the same central atom Y, so I have chlorine in both of these cases. And we had said if that's the case, the one that has the larger oxidation number on Y is going to be the stronger acid. And we had said we can just use the number of oxygen atoms as a kind of our shortcut to do that. So the more oxygen atoms it has, the stronger the acid. And again, that's assuming that we have the same central atom, right? I have chlorine in both of these cases. And I didn't really talk about the reason for that one. It has to do with the stability of the conjugate base, right? So comparing ClO3 minus versus ClO4 minus, this is actually more stable. And our reason for it is that the electrons are more delocalized. And delocalized is a word that you hopefully would have used in 150 or 151 when you were talking about resonance, right? We said that if a structure had resonance, it was more stable because we're delocalizing those electrons. We're actually spreading them out over the entire molecule or more of the molecule. Remember, chemical reactions are the reactions of electrons. So if electrons are sitting just in one spot, it's reactive because something can, grab onto those, or they can grab onto something. If they're spread out, right, if they're delocalized, so instead of being in a local spot, they've been delocalized, right, they're spread out, it's less reactive, more stable. So you can essentially draw more resonance structures for ClO4 minus. Its electrons are more delocalized, it's more stable. We want to form things that are more stable. This next one is also an oxo acid. This time I have the same number of oxygens, but a different central atom Y. And when that's the case, we said the more electronegative atom Y is going to be our more acidic one. And then this last one, selenium and arsenic are in the same period of the periodic table. When that's the case, we went with the more electronegative atom. So the bond between selenium and hydrogen is more polarized. It's going to be easier to break it than the bond between arsenic and hydrogen.